The kinetic fundamentals that we have covered in the earlier section of this lessons is related to the process that take place in the gas phase. But we as a chemist are generally more concerned with the reaction in solutions. So this topic here, we are going to look into some reactions in the solutions. And what's the difference about the kinetics in the liquid solutions compared to in the gas phase? Most of the added complications of kinetics and the rate processes in the liquid is come from the density of the liquid phase. In a typical gas at atmospheric pressure, the molecules occupy only 0.2% of the volume, whereby there are 99% is the empty spaces. So you will see that in the liquid, the empty space is much less compared to those in the gas phase. And what is the consequence is that with the more spaces available in the gas, so it will allow the reactant to move around much more frequently. While in the liquid solutions, due to the limited spaces available, so the solute molecules are in a constant collisions with either the reactant molecules or with the solvent molecules, which will cause the exchange of kinetic energy to occur. So solvent molecules may take up more than half of the solvent volume and massively outnumber the reactant solute molecule. These empty spaces in the liquid are irregular and it will be changed as the solvent molecule undergo the thermal motions, meaning that the empty spaces that is available in a volume is not at a constant, whereby it will be the empty space will change as the time goes. An encounter between the reactants in a solutions will occur in a very different manner from encounter in the gases, meaning that the reactant molecule that will bump into one another, the chances for the reactant molecule to meet each other will become different compared to when the reactions is occur in the gas phase. Reactant molecules have to jostle their way through the solvent. For example, in the image here, we have the orange balls representing the reactant molecule. So this reactant molecule, they have to move around the solvent molecule so that they can meet the other reactant molecule. And their encounter frequency is considerably less than those in the gas phase reactions. However, because a molecule also migrates only slowly away from their locations, and two reactant molecules that encounter each other, they will stay near each other for much longer time than the reactions that is occur in the gas phase. So if the reactant molecule has the chance to meet another reactant molecule, then the staying together for this molecule will be much more longer because they will need to have some time to migrate away from each other due to the presence of this solvent molecule. And this lingering of one molecule near another on account of the hindering presence of the solvent molecule is called the cage effect. So the time and the structure whereby the two reactants they bump into one another in the solvent, it called the cage effect, where they limit the movement of this encounter to move immediately, and the solute molecules momentarily confined to a hole within the liquid, and the time whereby this pair, reactant A and B, stay together is about 10 to the power of minus 11 seconds. This trapping becomes especially important when the solvent is strongly hydrogen bonded, as is the case with water or alcohol. And the confinement of this structure in the hole is become much more obvious if the solvent form the hydrogen bond, such as in water or in alcohol. When the thermal motions occasionally release a solute molecule from this trap, it will jump to a new location. And these jumps are very fast and short distance. So after the time, like 10 to the power of minus 11 seconds, in fact, the molecules will just jostle continuously. After some time, then they will be released from this hole and jump to a short distance and follow an entirely random pattern, which is called Brownian motion. So this actually is how is the molecule or the reactant molecule move in a liquid solutions due to the bombardment of the solvent molecule to the reactant molecule. So they will just keep on moving in the solvent. In a reaction, for example, reactant A meet or react with the reactant B to form the product. The reactant molecules will generally be jumping from one hole to another in the solvent mix. Only occasionally, a pair of the reactant end up in the same solvent cage, where they bounce around randomly and exchange the kinetic energy with the solvent molecule. So as I mentioned to you, the reactant A and B initially are dispersed in the solvent. And due to the motions of the solvent molecule as well as the reactant itself, they will have the chance for the reactants to come together, close together. And when it bounce into each other, they will stay together for some time in the solvent cage. So during this time, it provides the reactant to have some time to went through the process of exchange energy via these kinetic collisions. So the pair of the reactants which is confined to a solvent cage, we call it as the encounter pair. And the process can be represented as A react with B to form the encounter pair AB. And the activated complex. It can be known as the encounter pair or activated complex. So such encounter pair may accumulate enough energy while they are confined in this solvent cage to react even though it does not have enough energy to do so when it first formed. So meaning that even though when these two reactant A and B, when they come the first time when they come together, they doesn't have sufficient energy to react and form the product. While they are still confined in this cage, they will try to gain more energy from the surrounding in order to proceed to the formations of the product. So the two reactants will get multiple collisions at each other and greatly increase the probability that they will obtain the kinetic energy required to kick them over the activation hump before the encounter pair disintegrated. So this is a conditions which is a bit special compared to the reactions in the gas phase, whereby in the gas phase, when the two reactants bump together, if there is no reactions to occur, then they will immediately be separated due to the available of the empty space in the gas phase. But because of the presence of this solvent molecule, it confines the encounter pair into a cage. So due to this reason, then it will allow this pair to gain more energy from their surrounding for a certain period of time before it is disintegrated. So they will try to gain more energy from the surrounding and overcome the activation's energy to form the product. If they are successful to form the product forms will begins to move away from each other, and finally, after about 10 to the minus of 11 second or 0.1 femtosecond, the solvent cage will break up and the product diffuse away. So that is about how the reactions will occur in the solutions. The activation's energy of the reaction is much more complicated quantity in the solutions than in the gas phase because the encounter pair is surrounded by solvent, and we need to consider the energy that entire local assembly of the reactant and also the solvent molecule. So the encounter pair model introduced some new rare parameters. We will look into this in the coming few slides. We have the reactant. If we have the reactant A and B, it will form the encounter pair in the solutions to proceed to the product formations. So the first step is an equilibrium between the reactant outside and inside the solvent cage. And the rate constant Kd and Kd prime reflect those relating to the diffusions of the molecule through the solvent. And the values are strongly dependent on the viscosity of the solvent as well as the temperature of the reactions. So we have the reactant A dispersed in the solvent and reactant B also dispersed in the solvent. How frequent A can meet B? It depends on the diffusions of the reactant A and B in the solvent. So the rate of the diffusions is quantified as K subscript D to form the encounter pair. While the encounter pair, if it is not successful to produce the product, then it will be dissociate back to their reactant. Before we look into the rate of diffusions, we need to know what is the definitions of diffusion. Diffusion is the transport of a substance through a concentration gradient from a high region of the concentrations to a lower region of concentrations. So the example is the tea spread out when a tea bag is immersed in hot water. Diffusions occurs because random thermal motions of the tea. And eventually, the concentrations will become uniform throughout the whole cup of the tea, and it will achieve equilibrium. As the molecule diffuses through a liquid, the molecule must nudge neighboring molecules out of their way, and the work required to do this amount of nudge around the molecule is the activation's energy. Diffusion can be thought of a kinetic process with its own rate constant Kd and also the activation's energy. These parameters depends on the size of the solute, the size of the reactant molecule, and also the type of the solvent molecules where we disperse the reactant and how strongly the solvent molecule interact with each other. So all these will affect the rate of the diffusions. This suggests two important limiting cases for the reactions in the solution. If we have the reactant A and reactant B dispersed in a solvent, then the overall process can be divided into two simpler parts by setting up a simple kinetic scheme. And we suppose that the rate of the formations of this encounter pair AB is first order in each of the reactant A and also B. Then we can write the rate of the equations as given here, where the Kd with the D signifies the diffusions is determined by the diffusional characteristic of the A reactant and also the B reactant. The encounter pair can break out without reaction, or it can go on to form the product. If we suppose that both processes are pseudo first order reactions, with the solvent perhaps playing a role, then we can write the rate of the reactions to form the encounter pair as these reactions, and the dissociations of the encounter pair, if they don't form the product, they will reverse back to the reactant, and this is the rate of the reverse to form the reactants. Or if the encounter pair successfully produce the product, and we have the rate of the reactions as Ka multiply the concentrations of the encounter pair. So in order to find out what is the concentrations of this encounter pair, then we apply the steady state approximations where we assume that the net change of the concentrations for the encounter pair is equals to 0. Therefore, we have the rate change of the AB concentrations for the encounter pair with respect to time equals to 0, and we get these equations. And we rearrange these equations, we will be able to find out what is the concentrations of AB. The concentrations of the encounter pair is equals to the rate constant for the diffusions multiply the concentrations of the reactant A and also the reactant B divided by the concentration divided by the rate for the encounter pair to form the product plus the rate of the encounter pair dissociate back to their reactant. So the rate of the formations of the products from A plus B to give us the product is given as K2. So the rate of the product formations can be approximate to Ka multiply the rate for the encounter pair form, and it is equals to K2 multiply concentrations A and concentrations B. So K2 is equals to this piece of expressions if we compare these equations here with the equations given here. Okay, so this part here will be equivalent to K2 after we substitute AB into the equations. Okay, so we have this corresponding to the rate of the reactions for the product formations. There are two limits can now be distinguished. The first one is if the rate of the separations for the unreacted encounter pair is much slower than the rate at which it forms the product. The first case involved the dissociations of this encounter pair reverse back to their reactant if this rate Kd prime is much more smaller compared to Ka, or we say that the rate of the diffusions of the reactant molecules to form the encounter pair at the reaction site is much more slower than the rate of the chemical reactions to results in the product formations. Okay, so in this case here, if Kd prime is very small, then we can neglect this value and left only the rate of the whole reactions is related or approaching Ka multiply Kd divided by Ka. So Ka and Ka we can cancel out, left only Kd. So which means that if Kd prime is very small compared to Ka, then the reactions rate will depend on the Kd, which is how fast reactant A can meet reactant B. So in this diffusion control limit, the rate of the reactions is governed by the rate at which the reactant molecules diffuse through the solvent. Usually, the rate constant for this type of reaction diffusion control reactions is greater than 10 to the power of 9. And the activations energy for the encounter pair to overcome is much low. Rate of the diffusion control reactions is equal to the average flow of B molecules to all the air molecules in the sample. So it depends on how fast the molecule A or the reactant A meet the reactant B. When they meet, then they will immediately produce the product. The example of this kind of diffusion control reactions involve the combinations of the radicals, where it involves very little activations energy, and the radical and atom recombination reactions are always diffusion control. The rate of diffusion control reactions in a bimolecular reactions is calculated by considering the rate at which the reactants diffuse together. The rate constant for the reaction in which the two reactants molecule react, if they come within a critical distance R star, which is if we have reactant A and reactant B. So if these two molecules comes to a critical distance, or known as the reaction distance, then they will form the product. The rate constant can be quantified using the equations given here, where we have the 4 pi multiply the reaction distance multiply these diffusion coefficients for both of the reactant A and also B, multiply the Avogadro constant. So D here is the summations of diffusion coefficients for reactant A and also reactant B in the solutions. We can determine the diffusion coefficient through the Stokes-Einstein equations, where it relates the viscosity of the solvent and also the radius of the reactant A as well as reactant B. In this case, if we assume the radius of reactant A equals to reactant B, therefore it is also equals to 1/2 of the distance of these reactions. And if we substitute this 1/2 multiply the distance of the reactions into the diffusion coefficient for reactant A, then we will get Boltzmann constant multiply the temperature of the reaction over the 3 pi viscosity of the solvent multiply the reaction distance. Similar to the reactant B, we also can quantify the diffusion coefficient for reactant B using the same method. After that, we substitute the diffusion coefficient for reactant A and B into the rate constant for the diffusion for this D here, which is the summations of dA and dB. So after we calculate or we simplify the expressions here, then it will give us the rate constant for the diffusions equals to 8 multiply Boltzmann constant multiply T and also the Avogadro constant divided by 3 times the viscosity of the solvent. Okay, so this one plus this one has 2 kT over 3 pi viscosity R star. So R star cancel off. And then 2 times 4, we will get 8. Okay, so meaning that the diffusion coefficient will allow us to determine the rate constant of the reaction for the diffusion control reaction. So Kd is equals to 8RT divided by 3 multiply the viscosity of the solvent, and R is the gas constant. And in these approximations, the rate constant is independent of the identity of these reactants. So it depends only on the temperature and also the viscosity of the solvent. Again, the rate constant for the diffusion control equations depends on the temperature of the reaction and also the viscosity of the solvent. And it may be pointed out that these equations, the radius of the molecules have been cancelled out, and the bimolecular rate constant for these diffusion control reactions is independent of the size of the molecules for the reactant, while the rate constant of the reactions is inversely proportional to the viscosity of the solvent. By substituting the rate constant for the diffusion control reactions into the rate law, then we will get the rate of the product formations is equals to 8RT divided by 3 multiply the viscosity, multiply the concentrations of the reactant A and B. It's one of the example to determine the effect of the rate of these reactions if the reactions conducted in different solvent. So consider a non-ionic diffusion control reaction taking place in a liquid solution. Explain how the rate of the reactions for the reactants dissolved in ethanol would compare with the rate of the reactions for reactants dissolved in acetone. And given at 20 degrees Celsius, the viscosity of ethanol is 1.20 centipoints and the viscosity of the acetone is 0.32 centipoints. So basically this questions is relate the viscosity of the solvent with the rate of the reaction. The higher the viscosity of the solvent, the smaller or slower is the reactions. So for ethanol, the viscosity is higher than acetone. That means the reactions which is conducted in the ethanol will be much more smaller in the rate of the diffusions. Control rate constant. So the reactions will be much more slower compared to the reactions conducted in acetone. This is another example where you are asked to estimate the diffusion control rate constant for the recombinations of iodine atoms in hexane solutions as the solvent at 25 degrees C. And given that the viscosity of the hexane is 0.325 centipoints. So you can convert the centipoints into the unit SI. And you have to take note that in these questions, the reaction involved is iodine atoms. So iodine plus iodine will produce the iodine molecule. That's why it's called the recombination of the iodine atoms. So how to determine the diffusion control rate constant for these questions? The questions involve two reacting molecules which are the same substance, where iodine react with iodine. So we must divide the rate constant that we have learned just now, which involve reactant A and reactant B, which are the different types of the substance. We have to divide the rate constant by 2. Therefore, the rate constant to determine for these reactions involve the same type of molecule or substance. The equations that we use is 4 over 3 multiply RT divided by viscosity of the solvent. We do not use 8 over 3 RT divided by viscosity due to the same type of the substance reacting in this example. Okay, so we substitute the respective value of the gas constant, the temperature, and also the viscosity into the expressions. Then we will be able to determine the rate constant for the diffusion control reactions involve the iodine atom combined with the iodine atom. The result is given here. And this is the other limits for the determinations of the rate of the reactions, which is known as the activation control reactions. In these reactions, the rate constant for the product formations, Ka, is much more smaller compared to the rate of the dissociations for this encounter pair to dissociate back to the reactants. So we have the Kd prime is much more larger compared to the Ka, where the rate for the product formations from the encounter pair. So if Kd prime is much more larger compared to Ka, then we can neglect the value for Ka at the denominator. So the whole rate of the reactions is approximate to Ka multiply Kd divided by Kd prime. And Kd divided by Kd prime actually is the equilibrium constant. In other words, the rate of the reactions for activations control reactions is determined by the equilibrium constant. And in this limit, the reaction proceeds at the rate at which the energy is required to be accumulated in the encounter pair from the surrounding solvent so that it can proceed slowly to form the product.